Section 4.6 is a summary section, I guess I would call it in a lot of ways. We're going to pull everything together, things that you already know from precalculus, like asymptotes and asymptotes, intercepts, was the other thing I was going to say. And then we're going to couple that with everything we've now learned from the first derivative, increasing, decreasing, extrema, and second derivative, finding intervals of concavity and inflection points. So here's a graph, and we have to remember how to find all of it. So we need to be able to remember how we find those asymptotes, how we find all of our increasing, decreasing concavity intervals, inflection points, maxes, and mins. So we're just going to jump right in and go through some examples here. And we are going to start with, our first one is going to be f of x equals x over x squared minus 4. And as we go through this one, so our directions are going to be to find the domain. I'm always a fan of determining, I have been doing this for the last section or so, if there's a restricted domain, especially, we want to kind of identify that. We want to find any asymptotes to help complete the sketch as well. I might throw in the x and y intercepts as well. Determining increasing, decreasing, points of extrema, and then all the intervals of concavity and points of inflection. So let's take a look at the precalculus information to start. So we might be tempted to look at this one and think that we're going to have a situation where for our domain, potentially the denominator could go to 0. But if we tried to set that denominator equal to 0, we would quickly see that x squared plus 4, if you subtract 4, you get x squared equals negative 4, and then that's an imaginary solution. So the domain here is everything from negative infinity to infinity. So there are no values that make that denominator 0. So it might have been worth looking into, thinking about, oh wait, there's a denominator, and that denominator can't equal 0. But if you tried to set that denominator equal to 0 and solve, this is what I was kind of saying, if you try to take your square roots, this is where you don't get a real solution. So there are no values that make our denominator 0, so there's nothing to throw out. But that's kind of what you're thinking about initially. Okay, let's talk about asymptotes. So the first one would be any vertical asymptotes. So as we start to look at all of our asymptotes, I'm going to break it down here. So our vertical asymptotes are potentially where your denominator goes to 0 and your numerator doesn't. Where the denominator equals 0. But we just got done saying that if you tried to set your denominator equal to 0, you don't get a solution. So we have no vertical asymptotes in this one because those come from where your denominator would go to 0. Okay, your horizontal asymptote, this is the one, if you remember from your college algebra precalculus, breaks down into 3 cases. And this is the case, you're always comparing degrees of numerators and denominators. So in the situation that we're in here, the degree of the numerator, the highest power of the variable in the numerator is 1. The highest power in the denominator is 2. And when the degree of the numerator is less than the degree of the denominator, this is when y equals 0 is a horizontal asymptote. If the degree of the numerator is bigger than the denominator, there's no horizontal asymptotes. If they're equal, it's the ratio of the lead coefficients. And there's no slant asymptotes. That's if the degree of the numerator is exactly 1 more than the degree of the denominator. And so we don't have any slant asymptotes either. So it looks like just one horizontal asymptote in this case. All right, another thing that you might be asked to find, I didn't explicitly write this out in the directions, it's nice to plot some extra points, maybe the intercepts in particular. So if you were to find your y-intercept, remember that's where you sub in 0 for x and solve for y. And in this case, we would have 0 divided by 4, and that's just 0. So we get that our y-intercept is at the origin. That, of course, means it's also the x-intercept. But there could potentially be other x-intercepts. So if we're thinking about looking for x-intercepts in a situation where you have a fraction, well, you're setting your entire y equal to 0. So in this case, the whole fraction or function goes to 0 when the numerator goes to 0. And so again, it's just the origin in this case. There wasn't any others, but just to kind of review those processes there. All right, so that's all of our, I guess I'll call it my pre-calculus information. So on the next page here, let's start to look at all the information that we can potentially determine from the first derivative. So for our first derivative, we are going to need to use good old quotient rule. So our quotient rule is going to start with our denominator left alone times the derivative of the numerator, which is 1, minus the numerator left alone times derivative of denominator, which is 2x, all over our denominator squared. All right, so don't do the bad thing, which would be reducing the x squared plus 4s. You can't do that when you have this subtraction in the numerator. So all we're going to do, when you just have like binomials times constants 1 or times monomials, and here x times 2x is just 2x squared. So for really kind of simple quotients in the numerator, when you just have, maybe a little binomial, a couple monomials, all you're going to do is distribute and combine like terms. So our x squared minus 2x squared is just negative x squared, and then plus 4 all over our x squared plus 4 quantity squared. Okay, so this is our first derivative simplified. Okay, looks pretty good. Now we're going to look for our critical points. So we're looking for where f prime is equal to 0 or where our f prime does not exist. And a fraction goes to 0 when it's a simplified fraction like this, when its numerator goes to 0. So setting negative x squared plus 4 equals 0, adding the x squared to the other side. And then remember, when you take a square root to get rid of a square, you have to remember to introduce your plus or minus square root on the other side there. So x is going to be plus or minus 2. So these are two places, two critical points where f prime is equal to 0. Now maybe there's a place where the denominator would go to 0 because that would give us a critical point from where f prime does not exist. But this binomial squared goes to 0 only if the binomial goes to 0. And we've already discussed this, right? So if you subtract the 4 and then you think about trying to solve this by, again, taking a square root, your square root of a negative doesn't exist. That's a non-real result, so we don't get anything from that. So we have two values here that we're going to be including on our sign analysis. So as we kind of finish this first part out, we have our negative 2 and 2. We're looking to sub values into f prime so we can make conclusions about the original. And so let's sub in something less than negative 2. So maybe I sub in, probably negative 3. Remember, we're subbing into f prime. Negative 3 squared would be 9, but there's a minus in front of that. So minus 9 plus 4 would be negative in the numerator. The nice thing about this denominator, x squared plus 4 is going to be positive, and then you're going to square it, so it's definitely positive. So a negative divided by a positive is negative, and where f prime is negative, that means f is decreasing. And then we sub in something in between negative 2 and 2, so let's sub in 0. That gives me a positive in the numerator, and of course always positive in my denominator. Positive divided by positive, positive. So we are increasing. And lastly, subbing in something bigger than 2, like 3. So once again, negative 9 plus 4 would be negative divided by, denominator is positive. Negative divided by positive is negative, and where the derivative is negative, the function is decreasing. So we are going to have a little min, local min at x equals -2, and we're going to have a local max at x equals 2. All right, so in fact, if we wanted to actually maybe write this out as the ordered pair, this is going to be -2, subbing back into the original function, remember, f of -2, the original function was x, so -2 over x squared plus 4, so -2 squared. Of course, that's going to be 4 plus 4, so you're going to have 8 in your denominator. So -2 eighths, and then of course that would reduce to -1/4. So there's your relative min. And your relative max is at 2. Again, whenever you need that y coordinate, it's always back into the original function. So once again, 2 over 2 squared plus 4. So we're going to have positive 2 over 8. So, of course, a positive 1/4. So we have all of our information there, increasing, decreasing, extrema. And now I think that's all we can get from our first derivative. So now let's go on to finding some second derivative information. So as we go on to our second derivative here, our second derivative, I have to scroll down so I can at least see my first derivative up here. Let me create a little more space for myself here. All right, so let me first, I'm going to erase this, but let me just rewrite f prime over here, -x squared plus 4 over x squared plus 4 quantity squared. That way it's on the screen. All right, so working off of that f prime. So f double prime, again, quotient rule. We are going to start with our denominator left alone, so x squared plus 4 squared times derivative of numerator, which is -2x, minus numerator left alone, -x squared plus 4, and then times, times the derivative of the denominator, which is going to require our chain rule. So 2 quantity, x squared plus 4 to the first, and then times the derivative of that inside, so times 2x. And then this whole thing here is all going to be over our denominator, which is that binomial squared, quantity squared. All right, so from here, this is a pretty complicated looking second derivative. We're going to make our lives easier, and we want to start to observe, and here's really what should stand out to you. You have an x squared plus 4 in the denominator, and you have x squared plus 4s in both terms in the numerator. That is going to be your prompt to factor out a GCF. You're also going to be able to factor out maybe this 2x as well. We can maybe also factor out a 2x. So for these complicated either quotient or product rule situations, you want to factor out a GCF. So that's what we're going to do here. So we are going to factor out this 2x. So that is what came from, again, the monomial portion in both terms. And then we're also going to factor out an x squared plus 4. Now I can only factor it out to the first power because it's to the first in the second term. All right, what do I have now left in my first term? I still have the negative as part of that monomial, and I also have the binomial, one of the x squared plus 4s remaining. In the second term, so I have my minus. I have that little coefficient, that 1, 2 that was left there, as well as the binomial of -x squared plus 4. And this whole thing is over our x squared plus 4 to the 4th power. Now, we can reduce one of our x squared plus 4s. And essentially what we're going to do is we're almost there. We're going to just kind of clean up that larger quantity that was left here. So if you think about inside this larger set of parentheses, it would have been distributing through the negative, a negative x squared and a minus 4. Distributing through the minus 2, you'd have a plus 2x squared and a minus 8. So 2x squared minus x squared would just be an x squared, and minus 4 and a minus 8 is a minus 12. So that's what we would have there. And then that is all divided by, so this, this whole thing is what's simplified to what's in parentheses there. And then this is all over our x squared plus 4 quantity cubed. Okay, so this is our pretty good form of our second derivative. So nice and simplified here. Okay, so that kind of got sloppy up above here. I'm just going to kind of erase this part. So you saw where that came from. So at this point here, I'm just going to, I'll rewrite it real quick here. So this was my negative x squared, the minus 4, the plus 2x squared, and the minus 8. Okay, now we're looking for, of course, where our second derivative is equal to 0, or where our second derivative does not exist. And so we have a nice simplified fraction here. So looking for where, once again, the numerator would go to 0. It's already factored, so we can just jump right to setting each factor equal to 0. So we're looking for where 2x equals 0 and where x squared minus 12 equals 0. So obviously dividing by 2, we get x equals 0. And then adding the 12, we get x squared equals 12. And remember, you take the square root, you introduce the plus or minus square roots, and so we now have x equals plus or minus root 12 is fine. If you want to think of that as root 4 times root 3, then it becomes 2 root 3. But those are our critical points, well, critical points of the first derivative technically, because this is where the second derivative goes to 0. Possible inflection points, let's just call those that at this point. Possible inflection points we're going to put on the sign analysis to figure it out. So where the second derivative does not exist, for like the third time in this problem, it all started when we looked at the domain and potential vertical asymptotes, and then it comes up again in the denominator of the first and second derivative. And so once you've seen it, obviously you don't need to continue to rewrite it. But if you tried to set your denominator equal to 0, you end up with imaginary solutions, so nothing from that. All right, so we're at a point where I think we can jump into our sign analysis here. So our sign analysis, and this time we are subbing into our second derivative, but making conclusions still about the original function. And so we have the values at negative 2 root 3, at 0, and then at positive 2 root 3. So subbing in something less than negative, what was like root 12, well certainly negative root 16 is less than negative root 12, so I could sub in negative 4, and that would certainly be less than this value. You could always use your calculator, but that's certainly in that interval. So let's check out the second derivative up there that's kind of in the upper right boxed in. The monomial in front, 2 times negative 4, is going to be a negative. Negative 4 squared would be 16. 16 minus 12 would be positive in that binomial. And again, this denominator, something squared plus 4, is always going to be positive. So this is going to be a negative divided by a positive, which is going to be negative. Negative in the second derivative is going to tell me the original function is concave down. All right, something in between 0 and negative root 12 would certainly be negative 1. Again, subbing into the second derivative, 2 times negative 1 would be a negative monomial. Negative 1 squared would be 1 minus 12 would be negative in that binomial over a positive. Negative times negative would be positive, so we are concave up. And as we continue, again, it's tempting to always think that these things alternate, but we've seen that they don't. So subbing in 1, we're going to have a positive monomial times a negative binomial over a positive denominator. We're negative. We are back to concave down. And then subbing in something like 4 outside of or greater than the 2 root 3 or the root 12, that's going to be a positive monomial times a positive binomial over a positive denominator. So we are back to positive, which is concave up. All right, so what do we know? We know that at all of these values right here, we have, at these x values, we have an inflection point. So we have inflection points at each of these locations. And again, to get the y-coordinate, you'd be subbing those back into the original function. So I like 0. The original function, if you remember, that was the x over x squared plus 4. So remember, I'm just going to jot it off to the side here for a second. X over x squared plus 4. So sub in 0, 0 divided by 4 is going to be 0. If I sub in, I might work with the root 12 form. If I subbed in negative root 12 over negative root 12 squared would be 12 plus 4. That would be 16 in my denominator. And then I would have this 2 root 3 in my numerator. So I think this is going to come out to be, and you could go to decimals, especially for graphing purposes, but this negative 2 root 3 or negative root 12, and the y-coordinate looks like to be negative square root of 3 over 8. And then the last inflection point, again, 2 square root of 3. If I sub that in, that's like root 12. It would have been positive root 12 this time. Root 12 squared would have still been 12. 12 plus 4 would have been 16. This just would have been positive. So all the same values but positive. And again, I'd say, especially for graphing purposes, you're probably going to want to think about those, truthfully speaking, as their decimal approximations, right? So if we subbed those into our calculator, which I have my calculator here real quick. So my square root of 12, that's about 3.64. So this would be like negative 3.64 approximately. And your square root of 3 over 8 is approximately 0.22. So this is approximately 0.22. So I'll just put a big old approximately on these. So this would be approximately 3.64. That one was negative, and this is going to be approximately 0.22. All right, so just for purposes of graphing, that might be somewhat helpful to think of those inflection points that way. All right, so this is a lengthy process, all this curve sketching, all these facts that come together. And so let's take a look at kind of pulling all these pieces together, and then let's also look at the graph on our graphing calculator as well. In fact, let's maybe do that first. So let's take a look at this graph. Where did I put my graphing calculator app? Where did I put that? Where did I put that? Oh, here it is. Okay. Sorry, I should have planned ahead, but I didn't. All right, so let's put in our function, which is, again, the x divided by the quantity of, always imply parentheses in numerators and denominators, x squared plus 4. So this is our function, and so as we take a look, I'm just going to go to Zoom Standard, so number 6. And so this is a little hard to tell on this graph here because at least on the negative 10 to 10 window, it obviously, the min and the max values, you know, we're looking at some pretty small values here. In fact, did I find those? Let's take a look back on our function here. Yeah, 1/4, right? So that's why those values are so so low there, so small. But there's our graph. Let's maybe change that window. And so maybe we can get a slightly better view on this. Let's maybe just go from -4 to 4 on the x's. And then the y's, I think I'm just going to go from, the max is at a fourth, so a negative, so I'm going to go from -1/2 to 1/2. And let's take a look at that graph. So, as we look at this, I can pull this. Why did that go window? Oh, because I went to 5, not 1/2. All right, so this is looking a little bit better. Maybe on my x's, I should go out a little further, maybe -6 to 6, not 46 to 6. All right, so not bad. It is actually approaching. This will be enough for us to get a decent sketch here, but let's keep in mind what we know. We could trace through some values and find some things if we want to here, but let's keep in mind, I'm going to maybe pull this over to this side. All right, so let's take a look at coming up with a little sketch for ourselves. And so let's take a look at kind of off to the right here, because the whole point is supposed to be coming up with a sketch of the function. So as we take a look at this graph and kind of come up with our own little sketch here, let's be mindful of, we did have a horizontal asymptote. So I'm going to create a little bit of space here. At y equals 0. We did know from the very beginning there, we did know that the function was going to have an x and y intercept at the origin, so we were aware of that. And now the facts that we know from the increasing and decreasing. All right, so we know that at, let's say here at 2, we were up at 1/4. So this is not drawn to scale, but we know that we have a max at 2 1/4. And we know that over here at -2, again, I promise nothing here in terms of this being drawn to scale, but at -2, we had a min at -1/4. We also know we ended here with this inflection point at -3.6 and then like -0.22. So maybe this right here is an inflection point. And so let's actually get rid of this here, make this a little bigger. Okay, so as we think about extending, I hate it when I do that. Here, okay, so let's take a look at, this part is taking longer than I intended. All right, so at -3.64 and then approximately -0.22, that is going to be an inflection point. And so our graph actually starts, and maybe I'll do it in like just a slightly different color here. Let's just do it maybe in like a gray. So we are going to be approaching our asymptote. We are starting concave up. And then we go, so there's my, I'm sorry, we start concave down. We start concave down, and then it changes, and we're concave up until we get to 0, 0. So then from here, we are concave up. We go decreasing to that min, increasing, and this is going to be my next inflection point. And then I have another inflection point over here at, once again, let's say this is 3, 4. So again, 3.6 and then 0.22. So here approximately is my next inflection point. And so I am concave down, reaching this max all the way until I get to this inflection point. I'm concave down. And then at that inflection point, I change to concave up. So it is a subtle but important change. So I want you to kind of be mindful of these things as you're drawing your graph that these were, so I'm just even going to put next to it, that was my inflection point. And this here was my inflection point. So it should all come together as we're graphing. And again, we're approaching our horizontal asymptote that we identified in the very beginning here at y equals 0. So here's our x and our y-axis. So at the end of the day, we pull this all together, and here is all of our information on a sketch of the graph. Everything from the increasing, the decreasing, the local min, the local max, and those subtle changes in concavity drawn to the best of our abilities, and then also kind of using our graphing calculator as an aid in that. So that's a doozy. That's one problem. We will do a couple more of these over the next couple of videos.